So let us do another problem that was just like the problem that we did on Friday. And this involves the electrochemical cell. We have some equations here. I'll give you these equations on the test. So all you got to do is, I'll give you this. Really, it's just a matter for you guys to know which equation to use. Okay, this is the free energy. This is the E of the cell. F is a constant that's listed here. So, yeah. Okay, N is the number of moles of electrons that are transferred in the redox reaction. So all of these equations will be given to you on the test. So with that, we have to choose the right equation to do the problem. So this should be a same theme as the problem we did on Friday. So let's go ahead and do that. And I'll wait for this to zoom properly. And let's go ahead and start. All right. So calculate delta G for the following reaction at 25 degrees C. So I notice here that we have the delta G naught symbol. So this means it's at standard state. Okay, standard state conditions. That's what this little O means, standard state. Is it doing the blurring and not blurring with you guys? All right. I'm going to press this button, and then I'm going to press it again to see if I could stop the blur. Stop the blur. Okay. All right, so we have this equation here. The first thing you want to do is you want to split this equation up. Okay, we'll split it up into one reaction that's oxidation, one reaction that's reduction. Now you want to give it to Harrison. You want to pick this up. Give it to Michael over there. Also, it's just the same thing but better background. Oh, reach. All right, what I'm passing out is the same thing, but it's on a whiter background. So hopefully, it is my hope that you can see the numbers a little bit better. All right, so we have here aluminum plus 3 going to Al. So remember, the first thing we want to do is we want to split this reaction into its component parts. So let's forget the 2 for a moment. I'm going to just have Al plus 3. We'll have it in pink here. Go to Al. Okay. So the question to you guys is, how many electrons and where should we put it to balance this out? We have 1 Al and 1 Al, so the aluminum Al is balanced. But what do we need to do in terms of charge balance? How many electrons and where? 3 on the reactant. Okay, 3 electrons on the reactant side. Okay, so minus 3 plus 3 will make it 0 on the reactant side, 0 on the product side. And let's go ahead and figure out the voltage associated with this. So can you guys find it? Let's negative 1.66. Okay, I'll go by your word. I can't find it. Where's the bottom? Yep, I see it now. Negative 1.66. Do we flip it? No. Okay. Okay, is this the anode or the cathode? This is the cathode. Okay, this is the cathode. All right, let's do this in black ink. We have magnesium going to Mg plus 2. Okay. We're splitting this reaction, so don't worry about the numbers. They'll come back again. Don't worry about the coefficients. Magnesium going to Mg plus 2. Okay, how many electrons and where should we put it? Okay. Do you guys agree we should put 2 electrons on the product side? Okay, so we have 0 on the reactant side, plus 2 minus 2 is 0 on the product side, so 0 and 0. We have 1 mg here, 1 mg there. And let's take a look at the voltage. Let's check our notes here. 2.37, and you notice how Michael flipped it. Why do you flip it? This is being oxidized. Okay, plus 2.37 volts. He flipped the number that we saw here. Okay, because in this particular problem, it's the opposite reaction that's occurring. So when we flip it, we flip the sign. And this is the anode or the cathode? Anode. Well, obviously, if this is the cathode, Asia, then Leslie, the next one has to be what? You can't have two cathodes, or you cannot have two anodes. So, okay, so good. Nice job, both of you, or all of you. And so I'm going to cancel out the electrons. How many electrons should I ask you this question. I should multiply this by what number to cancel out the electrons? Times 2, and I should multiply this by what number to cancel out the electrons? Is 3 okay? So how many electrons are being transferred? This is a, how many? How many electron transfer reaction? This is a, how many? This is a 6 electron transfer reaction. Okay, this is a 6 electron transfer reaction. So let's go ahead and multiply the top part by 2. When we do that, we have 6E minus plus 2Al plus 3 goes to 2Al. All right, question for you guys. If I multiply this by 2, what happens to this number? Okay, very, very good. Stays the same. Excellent. And we'll multiply the bottom number by 3. So that's 3 mg solid goes to 3 mg plus 2 plus 6E minus, and you guys are correct. That number still stays at 2.37. Remember, those numbers, those voltages don't change. Okay, the only thing that changes is the sign. Okay, so 6E minus 6E minus, and we have our original equation here, which is 3 mg solid plus 2Al plus 3 this goes to 2Al solid plus 3 mg plus 2. Okay, we add these two reactions, we add their voltages, and I'm going to call this E cell because it's the anode and the cathode coming together to give you the battery. And what's minus 1.66 plus 2.37? I should be at 0.71. Okay. Positive, right? Positive. So is this spontaneous? Positive voltage? Okay. So this is a battery, okay, that you can make using magnesium and aluminum. So I'm just going to write here it's spontaneous. It favors the product side. Okay, it favors the products. Alright, so now we're going to calculate delta G here. And which equation should we use? You can pick one, anyone. I think I'm going to pick this one. You guys see this? Okay, which equation do you guys want to use? Well, we just calculated E cell. You guys did. F is a constant. What is N here? And this is how many electrons were transferred? 6. So this will give us delta G naught. So this is the equation that I want to plug and play. You know, plug and chug, plug and play. All right, so delta G naught. I'm going to use the second page here. delta G naught here is equal to minus NF E cell. Okay, this is the equation we will use. Okay, minus N is 6. Okay, this is a 6 electron transfer reaction. I think I'll just put 6 here. And then this is, F is, I'll give you this constant, 96,500 joules over volts, I think is how I'll write it down here. Joules over volts. Okay, this is the Faraday constant, and I'll give you that. You do not have to memorize it. Okay. E cell is, we just calculated that, okay, and we got 0.71 volts. Okay, the volts and volts cancel. You're left with joules, which is a unit of energy. Okay, so minus 6 times 96,500 times 0.71. What do you guys get? Shall we do it together? Minus 6 times 96,500 times E cell times 0.71. What is that? Minus 411,000. Okay. I'm going to divide it by 1,000 to make it in kilojoules. Okay. You can do 411,000 minus, or you can do minus 411 kilojoules. It's perfectly all right. Okay. And this is our answer. Okay. What does the minus sign tell you for delta G? Yes, it's spontaneous, but a word for spontaneous here with regards to delta G, we don't call it spontaneous, we call it exergonic, which is actually kind of the same thing as spontaneous, so you're right, but thermodynamic people will call it exergonic. Or exergonic, which means it releases free energy. So this will release energy that could be, I don't know, do the remote control on the remote control car or something. I don't know. Right, but it releases energy that could be captured and harnessed to do work. Okay, so this is exergonic. The positive voltage tells you that it's spontaneous. Everything aligns. Okay, everything corroborates one another, which is what you want to happen in these things. Okay. So now let's move on to another equation that I'll give you on the exam. You do not have to memorize this. This is called the Nerst equation. So what's the difference between the Nerst equation and the other equations that I'll give you? The Nerst equation deals with non-standard state. So that's the big one. Okay, this is any temperature, any concentration, okay? Non-standard state conditions, we will use the Nerst equation. So there's a natural log form and there's a log form. And then we have Q again. Okay, what is this Q? Q is called the reaction quotient. Okay, Q is called the reaction quotient. And we use Q and compare it to K. It tells us which way the reaction is favoring. Right? So if Q is greater than K, you want to put Q first. Okay, the alligator jaws are pointing this way, so this favors the reactants. Okay, probably you're not going to get a battery. Okay, no battery. Okay, the redox reaction favors the reactants. Or maybe I should say not no battery, because it favors the reactance, I'll say like a negative voltage, like a dead battery. Okay, and here we're going to get a negative volt. Okay, nothing gives you negative voltages. Okay, it's not going to give you the power. Okay, but if you have Q and it's less than K, the alligator jaws are pointing to the right, the product side. So this is a working battery. Okay, so this favors the products. And this will give you a positive volt. Okay, like the batteries we buy at Walmart. Okay, positive voltage. And then Q is equal to K. This is not a battery. This is not a battery. Excuse me. Neither are favored. Okay, so I think what is this? 0 volts. So this is the Q that we're going to use in the Nerst equation. All right. So this form or this form, I'll give you one or the other. They'll give you the same answer. It's just that this one has the natural log of the reaction quotient Q, and this has the log of the reaction quotient Q. All right. I'll give you the equation. Notice here to get E cell at the non-standard state, you need E cell at the standard state. Okay, you need E cell at the standard state when we plug it into this equation. All right, let's do an example of this in the Nerst equation, and the next several problems will have a Nerst equation. You get a lot of practice on the Nerst equation. All right, will the following reaction occur spontaneously at 25 degrees given that Fe plus 2 is 0.6, CD plus 2 is 0.01. So like we did before and like we're going to do from here and to the last page of our notes, we're going to split this reaction into oxidation and reduction. CD solid goes to CD plus 2. Okay, how many electrons and where should it go to balance this out? 2 electrons where? Products, very good. Okay, let's go ahead and figure out the voltage of that. Okay, what do you guys see when you do the cadmium one? Okay, is it going to be negative 0.40 volts or positive 0.40 volts? It's going to be positive, very good. This is the anode or the cathode? Anode? Anode, yeah, very good. All right, and let's do this in, let's pick a nice color here. Let's do the other one in wasting time. Kind of find a color that I'm in the mood for. How about red? Okay. All right, we have Fe plus 2 goes to Fe solid. We have Fe plus 2 goes to Fe solid. Okay, how many electrons and where should we put it? 2 on the reactant side, excellent. And let's go ahead and find what this is. I can see it already. You guys see this as negative 0.44 volts. Okay, negative 0.44 volts. Yes? Yeah. this is the cathode, right? All right. How many electrons are being transferred? This is a, how many? This is a 2-electron transfer reaction. Very good. So our net is going to be cadmium solid plus iron plus 2 aqueous. Okay, this is going to go to iron solid plus cadmium plus 2 aqueous. Okay, we'll call this E cell, and E cell is going to be what's 0.40 minus 0.44. Okay, minus 0.04 volts. Okay, so this is E cell. Okay, this is E cell at standard state. Okay. But these are non-standard state conditions. Okay, how do you know they're non-standard state conditions? Okay, look at the concentrations. Okay, the concentrations are not 1 molar. Okay, they're not 1 molar. So if they're 1 molar, that's standard state. So now we have this standard voltage of the battery, and we can plug that in here. Okay, and now we'll do the Nerst equation. All right, so now we'll plug into the Nerst equation. I'm going to move on to the next page here. This is one version of the Nerst equation I will use. And what is Q here? Okay. Q is going to be products over reactants. So products, CD plus 2, over reactants, Fe plus 2. Okay, why did I not add Fe solid or CD solid? Because they're solids. Very good. Okay. So what's the cadmium concentration? 0.01 molar. What's the iron plus 2 concentration? 0.60 molar. So what's 0.01 divided by 0.6? Is it 0.0016? Let's see how my brain is today. 0.0016 is what I'm going to say. Oh, I was off. 0.016. Okay. 0.0167. All right, so this is Q, which is products over reactants. Again, we're doing this. We already calculated that. And what is N here? This is how many electrons are being transferred? Very good, 2. So let's go ahead and complete this problem now. Okay, remember E cell, we calculated it already, and we got minus negative 0.040 volts, minus 0.0257 volts divided by 2, natural log of Q, which is products over reactants, concentration of CD plus 2 over Fe plus 2. This is 0.0167. All right, do you guys know how to do this whole thing in your calculator? Okay, let's do it together. Okay, first I would do natural log of 0.0167. Okay, times a minus. Okay, everyone see this? Everyone look, there's a minus here. So times a minus, check my calculator, 0.0257, close the parentheses, divided by 2, plus a minus. Everyone see here, plus a minus 0.04. So plus negative 0.04. All right, if I did this correctly, did you guys get 0.0126 volts? 0.0126 volts. Okay, good. All I need is one person to verify that I'm correct, and this is the right answer then. Okay, I'm confident. Right, so is this spontaneous or not spontaneous? The positive E cell tells you it's spontaneous. Even though at non-standard, at standard state, is it spontaneous? No, standard state is not spontaneous. But if you change or mess around with the concentrations, you can get it to be spontaneous. Very small voltage at 0.0126 volts. But again, this is spontaneous. All right, continuing on, lots of practice all the way till the end here. Page 11. Okay, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. Okay, 4 more Nerst equation problems. All right, you guys have the stamina and patience? All right, let's do this. What is the EMF of a galvanic cell consisting of cadmium CD half cell electrode and a platinum H plus H2 half cell if cadmium is 0.20, hydrogen ion is 0.16, and the pressure is 0.80 atmospheres if the reaction is to be happen spontaneously? Okay, so EMF just means electromotive force, and it's asking you to calculate volts, the voltage. So EMF just means electromotive force. And they want it spontaneous, so which means we're looking for a positive number. When we have the anode and cathode together, it should be a positive number. Right? So let's first write down the cadmium one. Where are you? Okay, here. I'm going to write it as is. Cadmium plus 2E minus goes to cadmium minus 0.40 volts. And we'll do the same thing for the hydrogen H2. Okay, I know this is 0, but I just know that. But it's right here. This is sort of like the baseline. Okay, don't let the platinum fool you, because it's a gas. The platinum collects on the gas, but the PT has nothing to do with the problem. So this is the second one. 2H plus 2E minus goes to H2 gas, 0 volts. Which one should we change to make this positive? We need to flip one, because both of these are cathodes, both of these are reductions. So we need to flip one to make it occur spontaneously. Which one do you want to flip? The top one or the bottom one? We're going to flip the top cadmium one. So we'll flip the cadmium half reaction. Okay, so this is going to be cadmium solid, goes to CD plus 2 aqueous plus 2E minus. We're going to flip it. And is this the cathode or the anode? All right, very good. This is the anode. Is this oxidation or reduction? Red cat eats an ox. Oxidation. We're going to keep this bottom one the same. Okay, is this the anode or the cathode? Okay, obviously the first one, cadmium, which we flipped, is going to be oxidation. This one we keep the same, and this is the cathode where reduction happens. Alright, so now how many electrons are being transferred in this reaction? This is a, how many? This is a 2 electron transfer reaction. So our net is going to be cadmium solid plus 2H plus. Aqueous goes to H2 gas plus CD plus 2. Okay, and this is going to be E cell now. This is E cell, and this E cell is going to be positive 0.40 volts. Alright, but this is not the answer because this is under standard state. We are not under standard state. We have this concentration of hydrogen ion. We have this concentration of cadmium. Okay. So let's see if under these conditions, what will the voltage be. So once again, we're going to use the Nerst equation. Okay, so this is E cell equals E cell standard, which we already solved for, minus, I'm going to use the natural log one, 0.0257 volts. This is a 2 electron transfer reaction, so 2 natural log of products over reactants. Okay. I should square that H plus. Everyone see why I'm squaring the H plus? I have to square the H plus because we have 2 of those. Alright, let's plug in here. We just calculated E cell. That is 0.40 volts minus 0.0257 volts divided by 2. Natural log. What's the cadmium ion concentration? 0.2, everyone see that? What's the pressure of hydrogen? 0.8. And what's the concentration of hydrogen ion? 0.16. We have to square it. Products over reactants. Okay, we never put solids. All right, are you guys okay in doing this big swath of math on your calculator? All right, I think I'm going to do it in one step. I'll see if Allison or anyone else can verify this for me. 0.2 times 0.8 is 0.16 divided by 0.16 squared is 6.25. Okay, I got this. I'm going to take the natural log of that. I got that. Times, everyone look, this is times a negative 0.0257 according to the equation. Times a negative 0.0257. Okay, I'm going to divide it by 2. Okay, divide it by 2. Because this is a 2 electron transfer reaction. And then plus, everyone see here, plus a 0.40. Plus a 0.40. Okay. I'm getting 0.38 volts. 0.38, anyone got it? Okay, got one person who got it. So I'm going to say this is the right answer. All right, so this is how we do this problem. Okay, the Nerst equation. Okay, so if you play around with the concentrations and the pressure, you can get this from going to 0.4 volts to, well, this is even better at standard state than it is under these concentrations and pressure. Standard state is 1 molar and 1 atmosphere. Okay, standard state is 1 molar and 1 atmosphere. It's 1 molar, 1 atmosphere. All right, let's go ahead and move on here to the next one. Let's see if we can squeeze in 2 more, or at least finish this one before class is over. All right, so consider the following cell diagram. Okay, do we know how to read one of these? Okay, so we have here magnesium, a straight line down, and magnesium sulfate. All right, so we have here magnesium, solid, straight line down, magnesium sulfate, whose concentration is 0.40 molar. Okay, so this is the anode. Okay, anode. We put 2 lines down. Okay, this symbolizes what we're going to call a salt bridge. Okay, something that connects the anode and the cathode together. It's a salt bridge. And then we have the cathode. Okay, anode couple, salt bridge, cathode couple. Okay, 0.60 molar, Ni solid. This is the cathode couple. All right, so can anybody see what the spectator ion is in all of this? SO4 minus 2 is the spectator ion. Okay. So in the anode, we have Mg solid going to Mg aqueous. And what's the charge of the Mg aqueous? Plus 2. Okay, this is Mg going to Mg plus 2. Now, how many electrons and where should we put it? 2 where? Products or reactants? Products. Okay, let's see what that is on our table. Magnesium plus 2 electrons. Here we go. Okay, what voltage should we put here? Positive 2.37. Very good. Okay. Is this the anode or the cathode? This is the anode. Okay, and then the next one will be nickel. Going to nickel solid. Nickel plus 2. Because remember, this is Ni plus 2 to SO4 minus 2 ionic. And Ni plus 2 goes to nickel solid. How many electrons and where? 2 electrons reactant side. And what is that voltage? Negative 0.25. Is this the anode or the cathode? Cathode. Okay, so we're going to add these up together. How many electrons are being transferred in this reaction? This is a 2. Very good. Thank you. This is a 2 electron transfer reaction. This is a 2 electron transfer reaction. So 2e minus cancels, and we're left with nickel plus 2 aqueous. plus magnesium solid goes to Mg plus 2 aqueous plus nickel solid. And we're going to call this E cell now. And what's 2.37 plus a negative 0.25? 2.12, am I right? Yes? Okay, good. 2.12 volts, okay? So that's at standard state, okay? But we're not at standard state because we have magnesium plus 2 at 0.4 and we have nickel plus 2 at 0.6. Okay, so we're not done with the problem, not yet. What we'll do is use the Nerst equation to figure out the voltage at this concentration. Okay. At this concentration, not the standard state concentration, which would be 1, but this concentration. All right, so the Nerst equation, I'm just going to copy it from our notes. Okay, let's fill stuff in. E cell is equal to 2.12 volts minus 0.0257 volts divided by N, which is 2, natural log of Q, products over reactants. So it's going to be the concentration of Mg plus 2 divided by the concentration of nickel plus 2. Okay, everyone see that? See this? Okay. And we know one of them is 0.4, the other one is 0.6, so let's go ahead and plug that in. Okay, 0.40. Nickel plus 2 is 0.60. Okay, can we do this on our calculator? All right, let's do this on our calculator. 0.4 over 0.6 is 2/3. Okay, and the natural log of 2/3, okay, is negative. Okay, everyone see, I'm going to take that natural log of this, multiply it by negative. You see that? There's a negative there. Negative 0.0257. Okay, we're going to divide that by 2. You'll see, we're going to divide it by 2. All right, plus the 2.12, okay, which is E cell. Not much of a difference here, 2.13 volts, okay, if you round up. All right, in part B, we will decrease magnesium by a factor of 4. Okay, let's go to part B and finish this off. How does the cell voltage change when the magnesium is decreased by a factor of 4? So when you decrease it by a factor of 4, this is no longer 0.4, but what's 0.4 divided by 4? Okay, 0.1. So all we got to do to solve for part B is replace 0.4. Magnesium has gone down times 4, so 0.4 divided by 4 is 0.1. So we plug everything in, but instead magnesium has decreased from 0.4 to 0.1, down by a factor of 4. All right, so we're going to do the exact same thing. Remember, went down by a factor of 4 in this problem. All right, so let's finish this off here. Natural log of 0.1 over 0.16, 0.1 over 0.6. We'll take the natural log of that. Okay, so that's minus So minus times, look here, everyone, minus times a minus 0.0257 times a minus 0.0257. Okay, that's that number. We're going to divide it by 2. And then positive 2.12. Positive, getting about 2.14 volts. Okay, 2.14 volts. So actually, if you want a little bit more of an increase or an output in your voltage, small amount, you can decrease the magnesium. Okay? Decrease the magnesium ion concentration, and you can get a slight uptick in your voltage. Slight one. Okay? Because 0.4 molar magnesium is 2.13, 0.1 molar magnesium is 2.14.